Random forest is all random, and that each tree is has no dependencies. And what I find interesting is that this random pick with replacement. I don't know why it works well compared to like it without replacement and just take the example in one. And the XG boost, and when it announced, I heard lots of buzz. I did not spend the time to learn at that time. And I heard lots of good news and good things. And I did try it recently, and the performance is kind of slow compared to LightGBM. And I look up what's the reason is that mostly related to how it is split the tree and how it is grow the tree. The problem with speed is that it first need sorted, and the sorted is a logarithmic algorithm, and it take quite a lot of time. And it also need to store those data. And the cache is not always hit, so it takes kind of long to train it. Relatively, that LightGBM, they have few innovative idea, and it's much faster. And the four main idea is that it's using histogram, and then it's leaf-wise grow, and then it's gradient-based one-sided sampling and feature boundary. And it's much faster. The idea is that the histogram then can combine the values into bins. For example, 256 bins, and then can split on leaves, not like XGBoost is by the levels. By leaves mean that it can pick which is the best leaf to split. And gradient-based one-side sampling that can keep the largest gradient, but sample the smaller one. And sometimes we have lots of features, they are just sparse. If we bundle it together, then the amount of features is much smaller, so we can make a time much faster. And when that we using all those tricks, and the memory becomes more packed compared to XGBoost, and that's will make it much faster. So here is a bit more like how histogram-based works. So we have a value, and the value will first will be get sorted like this. And then once sorted, we need to find how to split two different bins. And I using very simple bin split in my code, but the LightGBM, they have more aware of like quantile wise and whether its data is too dense or sparse. So the split value is not even distributed. I just using even distributed. So once find the bin split, so they will map the value to a smaller bin value. Typically will be 8-bit. And later on, when we use that 8-bit, is much faster. And interestingly, now XGBoost also support histogram-based splitting. And XGBoost is typically that they support the called level-wise growth. So the trees are balanced. And on the other side, that the LightGBM is using leaf-based, which means they can just pick what's the largest gain node and split on that node. So the tree is usually not balanced. And XGBoost also support that using by one feature tag. And GOSS might be the most interesting thing in LightGBM. So they do the sampling. So if we order that, and from the high gradient to the low gradient, then we pick certain percentage. By default is 20% of the topest gradient, and sample the rest part of 10%. Then we can times the ratio, like times 8 back, so the total gain will be roughly the same. And in this way, that when we build the histogram, we only need to take 30% of data, but it's still able to preserve good amount of gradient information. And quite often that, like, for example, this one hot encoding that like certain things will be split to multiple columns. But this feature bundling, they might able to do it to like make it back in one feature, not necessarily from one hot encoding, but as long as those features are not conflict each other, and they can put into one. And I find that this is interesting when hot encoding and feature bundling means no one hot. And I search the market space of LightGBM is by far those normal machine learning algorithm to be used. And the LightGBM, I think the most important is that all the companies I worked, they are all use LightGBM. All those companies, those tabular data I have in HM and Truecaller, and before at Tele2, they all using LightGBM. The reason is that those tabular data is using LightGBM is so easy and get very good result. Some company has tried to using neural network, and what I heard is that it's very hard to get the beat of those decision tree based algorithm. I have not heard a concrete case that they have done good thing compared to using neural network or decision tree based. And the different decision tree based, it's a bit difference, like the training speed is one for LightGBM, and it's also relatively using small amount of memory, like around a quarter of the memory something. And they also support the good parallelism, so you can using GPU as well. And in my implementation, I don't using GPU. And roughly, I think compared to XGBoost might be around 10% of the time something. And though that I think in company-wise, sometimes the training speed is not important, but if we're training like multiple hours, and it makes sense, we can see the result much faster. And there are many real-world use cases. What I heard is like those churn predictions and lifetime value, those things, all very good using decision tree based. So my implementation of GBM is roughly around 600 lines of code in PUC, and I only support the single threaded. And the performance, I only do very small performance comparison, so roughly like 60% of LightGBM also. If I spend I think around a week to try to optimize it. And that's the result I get. And got some ideas. If I have time, I will try to optimize more. So it might achieve a comparative performance with LightGBM. So it is working like this, so that I get the CSV data. I just pick a cargo data set and then have a data set file and try to put into a bin format. So it's a column-based bin format for each features. Then train it, and train it, then we'll get the result and save as the model. And this is how the code look like. So I have one header file to define all those structures and have the data set. That's the first step. I will pass the CSV file and save as the column-based. And here I included the histogram-based bin as well. So when save the featured data set, it will become a bin-based column. And the model is where to train it, like how to create the map, how to find the split. By the way, the code is on GitHub. You can look up, and it's not very complex. And the utility is few print out, so I can have a more colorful print out for here. I like using memory map and here as well. So when I first do it, I just load everything into memory and then scan sequentially from beginning to end. And how to load the memory is decided by the operating system. I don't need like, if I go back again, then I need to read again. So I just put everything into the memory map. If I read with a file, then I need to handle like the cache, how to go there. But using map, I just don't need to do it. So remember, the operating system will handle it, everything for me. And using row-based compared to column-based, so we can normally CSV is by row-based. So, but if we're doing machine learning, quite typically we're using column-based. And the column-based also, not only the memory is become more compact, but also that the catch hit is much higher than using row-based, because we can do one feature at a time. And so each feature will just go through as sequentially. And the performance is much faster compared to using row-based memory. And then the bin mapping is first analyze how the data look like, and then try to set the boundary. And from the boundary, we'll get an 8-bit value. And so the memory size is will take from roughly like if we zoom float, will be from 4 bytes become to 1 byte, 1 byte. So the memory is like a quarter of the size. And here is actually not only save the memory, because now the performance is not really the CPU bounded, but the memory bandwidth bounded. And I have added some of the adaptive encoding as well. So if the amount of value in a feature is smaller than like 8 bits, then we don't need using all those 8 bits. And again, we can using a less amount of bit to represent the value. So like 2 bits, 4 bits, very similar with nowadays the large language model using quantized version. And the histogram building is one of the main time spent. So we go through all those histogram and try to calculate the gradient and the second level gradient, the Hessing. And from there, we can find where is the best split. We just need to look at one of the largest gain node and then go through each features and see that which feature has the best gain split. When we do the GOSS sampling, and we pick the top 20% of the gain node and the rest of the node. But if we need to order it, it will take a logarithmic time. There is another algorithm called quick select, because we don't need a node order, but just pick the top gradient. It can get linear time. So just need to scan once and get it. So the GOSS is just the first quick select, the top 20%, and for the rest part, take the sampling. And then we can times together. Compared to XGBoost and LightGBM is using leafwise. So we always try to get the toppest gain from pop from the heap. And then we do the partition and then we add to the tree node. And after that, I have some comparison. So roughly is training time is a bit slower than that. And the size, because when I read the LightGBM code, is massive. It's very hard to follow how it goes. But I want able to like stepwise through, so I can just using this small code base and try to go see and how it goes. We can run another test here. So how I do it, so make compare. And data set is here, so the house price. And we have the tree build, and the root mean square error is this one. And interestingly, that LightGBM is a bit higher than my implementation. And the LightGBM takes 20 milliseconds, and my implementation take 40 milliseconds. So the difference is that LightGBM, the reason is fast because it's using the histogram-based, and the bean only need to build once before the training, not need to do for every tree. And it's leaf-wise grow, and it's better accuracy, but sometimes it can be get overfitted. And it's using GOSS sampling, so it can reduce large amount of data during the build the tree. And the feature bundling, it can be smaller, pack different features into one, so we don't need to scan all those features. And this on the other side mean that we should not using one hot encoding when we do decision tree based, because those will make things much slower. And we do implementation this I using zero copy IO and using column based catch. And adaptive bin can further reduce memory and make the memory bandwidth less bounded. And using quick select, for doing those top gain nodes. And I also add a bit of the LightGBM visualizer. So if we have a model trained, we can visualize it to based on a tree. So this one has 100 trees, and this is the sample data set. So I put it here, and I can go over to each tree to see how it is splitted. It's made a bit harder to read. Like each one has the condition on which feature. If go there, and something will goes to different node. And in the last, it has amount of sampling. How many sampling? Like this one have 23. This one you can also access it. And if you have different model, it need to be using text format, and you can drag in. It will be able to render the tree. I will say thank you. And if you're interested, you can take a look what I am doing on this Object Explorer. And this I writing some small reinventing my wheels there. And my LinkedIn profile is welcome to get connected.